We present GLIB, a method for efficient exploration for relational model-based reinforcement learning. Exploration is a fundamental problem in reinforcement learning. In model-based reinforcement learning, the agent must explore its environment to gather data for improving its transition model. This model can then be used to plan for achieving goals or maximizing rewards. We focus on relational model-based reinforcement learning, where states and actions are represented as logical formulas. One way that exploration or curiosity manifests in human children is by trying to achieve specific things in the world, such as climbing onto a counter or taking a cookie without being caught. GLIB is inspired by this mode of human cognition. The high-level idea of GLIB is that the agent repeatedly sets specific goals for itself and tries to achieve these goals. This is in sharp contrast to traditional exploration methods in AI, which typically are not focused on the relational setting and do not involve look-ahead or goal setting. The GLIB algorithm repeatedly samples novel goals, trying for each one to plan with it under the current model that is being learned. When a plan is found, the agent simply executes it in the environment. This exploration method naturally benefits from deficiencies in the model, because any time a plan has unexpected consequences, we know that we're getting useful data for improving it. GLIB is defined by two hyperparameters. The first is whether the goals are lifted like an existential formula, or ground, as shown in this example. The second is a maximum size for the conjunctive goal formulas. Let us now walk through an example of GLIB in action. A robot starts off in a grid world containing locked rooms and keys. Picking up the key of a particular color removes the locks or colored walls of that color. At the start, the agent has no model of the world, so it takes a random action. This causes it to update its model for the move action, which now states that moving somewhere would change the value of the at predicate. At some later time step, the agent babbles the goal of being at a key, resulting in the plan shown here. But when it executes this plan, it picks up the key, causing it to learn a model for the pick action. At an even later time step, the agent babbles the goal of being inside a locked room. When it tries to do so, it fails and realizes that it must again update its model for the move action to add a precondition stating that the room it is moving to cannot be locked. In experiments, we see that GLIB performs extremely well. These plots show average planning success rate on a test set of goals across various domains. The black curves are an oracle exploration method that has access to the true model. In all domains, either ground or lifted GLIB significantly outperforms all the baselines, which include state-of-the-art relational exploration methods iRail, Expo, Rex, and ILM. Similarly, we see that the raw one-step prediction error rate of the learned model usually decreases more quickly with GLIB than with any of the baselines. Thank you.